Hi everyone, my name is John Paul, and today I'm here to talk about POET, an interactive spatial query processing system in Graph. So this work was done in collaboration with Liang and Tianyuan at the Graph AI lab, which is a joint lab between NUS and Graph. And the work was done under supervision of Associate Professor Bingsheng from NUS and Sien and Feng from Graph. Now, the growth in ride-hailing and food delivery services, along with the widespread adoption of smartphones, have led to the collection of large amount of trajectory data. And the analysis of this trajectory data is key to companies such as Grab to help improve their services as well as vehicle routing and to minimize congestion. Now, interaction-based systems are an efficient way of analyzing this data due to their ability to due to the ease of expressing the queries in these systems. For example, in these systems, a user can express complex queries simply by interacting with the system instead of having to issue complex SQL statements or Python scripts. So the use of the interactive GUIs for analytical query processing provide these interaction-based systems with a unique opportunity to begin processing of the query as they are being expressed by the system, expressed by the user. This is because unlike traditional systems, these systems do not have to wait for the user to supply the entire set of instructions. These systems can interpret the user intentions ahead of time and then begin execution as the query is being expressed. In spite of this, all existing interaction-based systems fail to take advantage of these opportunities and adopt a process after query approach where the query is executed only after the entire set of interactions from the user is complete. This leads to significantly higher response time and inefficient use of resources in these systems. To address these challenges, existing interaction-based systems need to move to a process with query approach, where the processing of the data begins before the user finishes expressing their intentions. This can help ensure more efficient use of resources and can reduce the response time significantly. However, such an implementation is not trivial and is challenging due to the need for prediction of user intentions from a small subset of user interactions and the need for a progressive execution of the query plan itself or the spatial operators. To demonstrate the benefit of demonstrate the benefit of progressive execution in modern interaction-based systems, we present an example which is very common at Graph. In Graph, in spite of the improvement in the mapping data availability in different regions, there is still regions where the mapping data is incomplete. So in these regions, certain segments of the road might be missing. An engineer in Graph can identify the segments by simply focusing in on the relevant region and then drawing a trajectory where they suspect a missing trajectory. Now, if the existence of large number of trajectories similar to this reference trajectory in the underlying dataset would represent that the road segment is missing. Now, typically a system that adopts process after query approach will have to wait for the user to express the entire query before fetching the trajectories from the underlying dataset and then computing the similarity, which is highly inefficient. While a process with query system can begin processing of the data as the user is drawing the trajectories and can return similar results, similar trajectories as soon as the user finishes drawing the trajectory, significantly improving the response time. Now, overall, the design of POET consists of two major components: an interactive client, which is running on a touch or pointer-enabled device, and a high-performance query execution unit, which is executing on remote clusters. The interactive client is responsible for predicting the user intentions from a subset of user interactions, while the high-performance query execution unit is responsible for enabling progressive execution of the spatial operators or the query plan itself. The prediction in POET is done by what is known as an interaction prediction engine. The interaction prediction engine, or the IPE, is responsible for predicting the future user interactions based on the past interactions. For this, we make use of past studies and adopt a Markov chain based model. So the IPE makes use of a Markov chain, which is also referred to as a user interaction model, or UIM, in POET, and then predicts the future interactions. So a UIM, or the Markov chain is simply a sequence of possible events in which the probability of the next event depends on the past n events. Now, the prediction process in POET consists of two key stages. The first is calibration stage, which is typically conducted when a user is added to the system. During this stage, the UIM is being built by the system, and the probability of transition from one state to another in the UIM is determined. This is done by asking the user to express a predetermined set of queries, and then the prediction stage, which is performed constantly as the user is interacting with the system. During the prediction stage, the system is provided as input a UIM or user interaction model, an ordered sequence of past interactions, and a probability threshold. And the system provides as output the longest sequence of future interactions with a threshold higher than the with the probability higher than the provided threshold. Now, moving on to the progressive execution, which happens on the remote clusters. The progressive execution engine in POET is designed to execute the entire query plan or the spatial operators progressively. That is, the data will be processed as the query is being expressed by the user. The progressive execution engine is designed to minimize the cost of mispredictions, as well as it is designed to efficiently handle repeated updates to the operator parameters. This is because due to the predictive nature of the system, mispredictions are bound to happen. Further, parameter updates would also happen in any system that adopts a progressive execution scheme. And the overhead of these two needs to be kept to a minimum. To achieve this, we adopt two key policies. First, the additional number of data objects that are fetched due to an update to an operator parameter, it will not include any data objects that are already fetched by the system. And the second one is that the system ensures that the number of data objects that needs to be reprocessed as a result of the parameter update is kept to a minimum. So overall, POET consists of three key progressive operators, and the two major ones are the trajectory similarity search and the spatial join. The trajectory similarity search operator simply identifies the trajectories that are all the trajectories that are similar to a reference trajectory, while the spatial join identifies all the trajectories that are passing through a specific polygonal region. Now, the trajectory similarity search operator in POET is triggered by simply focusing in on a region and then drawing a trajectory, while the spatial join is triggered by focusing in on a region and then annotating the region. To enable progressive execution in the trajectory similarity search, the trajectory drawn by the user is broken down into segments and then processed, and the similarity of each segment with the underlying trajectory dataset is computed progressively. While in the spatial join, the polygon that is being expressed by the user is updated progressively or refined progressively to enable progressive execution. Moving on to experiments. For the experiments, we use a Sien E5-2698 V4 CPU with 20 cores operating at 2.2 GHz. The system is also equipped with 256 GB of RAM. For the processing, we use 418K trajectories obtained from Grab, and as a test case, we use two commonly used scenarios in Grab, S1 being the scenario 1 or S1, where the data engineers try to understand the trip patterns to or from a specific region, and S2 or scenario 2, where the data engineers try to identify missing route segments. Now, looking at the evaluation of the predictive execution in POET, we first look at the impact of the order of the Markov chain on the accuracy of the prediction engine, or the IPE. And we can see from the graph on the right side that a Markov chain of order 3 performs reasonably well for the specific use cases in Graph. It achieves reasonably high prediction accuracy while also keeping the overhead of the training and the prediction process to a minimum. Overall, by using a Markov chain of order 3, POET is able to achieve a prediction accuracy of above 80% for both S1 and S2. Now, in the case of the progressive execution, as we mentioned before, due to the predictive nature of system, mispredictions are bound to happen, and the parameter updates are also inevitable. This means that progressive execution would add some amount of overhead due to the additional processing required to handle these two scenarios. In spite of the frequent mispredictions and the frequent parameter updates, POET is able to keep the overall overhead of progressive execution to less than 15% for all the operators which are currently available. Overall, POET helps improve the latency of query processing by up to 25 times and improve the overall performance by up to 1.7 times. These values are in comparison with TRAVI, which is the previous interaction-based query processing system used at Graph. Now, the improvement in the overall performance is significantly lower than the latency because the improvement in the overall time includes the time taken by the user to express the query, which cannot be optimized. Now, in addition to both S1 and S2, we also look at two scenarios referred to as S1 dash and S2 dash when looking at the overall performance improvement. So these are same as scenarios S1 and S2 without a temporal filter. This means that the progressive and predictive execution POET helps improve the performance even for relatively simpler queries. Overall, we have already demonstrated in the study we demonstrated the inefficiency of existing interaction-based systems that adopt a process after query-based execution approach. To address this, we propose POET, an interaction-based query processing system which adopts predictive and progressive execution. Through the efficient use of predictions and progressive executions, we are able to reduce the latency of query execution by up to 25 times and improve the overall performance by up to 1.7 times.